Okay, then hello. Hopefully, all of you are well and safe during this unfortunate pandemic. First of all, as Hyperloop Manchester, we are very glad to welcome you to our first ever masterclass. Yousef and I will deliver today's masterclass, which is an intro, simply an intro to power electronics. To introduce myself, I'm Hakan, co-president and electronics team advisor of Hyperloop Manchester. And Yousef is on the call as well. Yousef is one of our brilliant members in electronics team. Say hi, Yousef.
Hello.
Yeah. Okay. So yeah, this is our syllabus of Power Electronics Masterclass series. So we will reveal the topic of each next masterclass week by week. So at the end of today's masterclass, you will know the topic of the next Power Electronics Masterclass. Our Power Electronics Masterclass series planned to be seven videos in total. 4 of them will be placed during semester 1, and 3 of them will be held during semester 2. Please have a look at the date of each masterclass in detail by taking a screenshot of the current slide. I can give you a few seconds to do that if you want. And as you can see on slides, masterclass days of semester 2 will be specified by the beginning of semester 2. They are not certain yet. Okay, I hope that you have taken screenshot or like taken your notes. Yeah. Okay. Yeah. So let's talk about the definition of power converters and their main responsibility. What are power converters or switching converters? They are simply the brain of power systems. They allow the conversion of the voltage and current levels with high efficiency. They also allow the control. There are various types of the conversions. First, DC to DC conversion, which changes and controls only the voltage magnitude since it does not change the type of the signal. AC to DC conversion, which controls DC voltage and AC current. DC to AC conversion, which creates sinusoid of controllable magnitude and frequency. Finally, AC to AC cycloconversion, which changes and controls not only the voltage magnitude but the frequency. We will cover all of these conversions later on in this presentation. So why do we prefer to use power electronics and not create an alternative way for that specific use? Simply, what are the benefits of using the power electronics? There are 2 key features of power electronics: high controllability and high efficiency. These 2 features will be covered in detail in the next slide, so we will just go through it for now. In addition to those 2 key features, the power electronics do not usually need maintenance compared to all related methods. They also weigh low and are small sized, so they are easy to use. They don't require any special or specific environment settlements to be used. They do not create acoustic noise, which is one of the main reasons of their high performance and efficiency. Finally, they cost low on the market, so they are budget friendly as well. So now let's talk about the aforementioned 2 key features: high control and high efficiency. For the control of the power converters, traditional analog feedback is usually preferred. You can see the diagram here. It is like a generic diagram of the control of power converters. So it's a general diagram. Moreover, it is possible to create a sophisticated control in power converter circuits using inexpensive digital microcontrollers. The converter circuits create a convenient circuit environment for the high control as well. On the other hand, high efficiency leads to low power loss within the converter. In this way, small size and reliable operation become feasible. In general, converters are loss limited, and technologies that can produce large power output while incurring small loss mostly result in small size and cost. thanks to this feature of power converters. Now let's talk about the specific types of power conversions, starting with AC to DC converters, aka rectifiers. Rectifiers are electrical devices that convert AC, alternating current, which periodically reverses direction, to direct current, DC, which flows in only one direction. So yeah, AC to DC converters can be used in home applications such as mobile phones, chargers, and etc. On the right hand side, you can see the rectifier types. Clearly, there are two main types of rectifiers: half wave and full wave rectifiers. For the most power applications, half wave rectification is insufficient for the use of purpose. The harmonic content of the rectifier's output waveform is very large and consequently difficult to filter. Furthermore, the AC power source only supplies power to the load one half every full cycle. So this means that half of its capacity is unused. Half-wave rectification is, however, a very simple way to reduce power to a resistive load. So it's a simple use. But if we need to rectify AC power to obtain the full use of both half cycles of the sine wave, a different rectifier circuit configuration must be used, which is a full wave rectifier. One kind of full wave rectifier called center tap design uses a transformer. You can see center tap design circuit diagram here. Uses a transformer with a center tap secondary winding and two diodes, you can see there. Another more popular full wave rectifier design is bridge rectifier. It is built around 4 diodes, bridge configuration. A bridge rectifier does not require a bulky centered tap transformer, since the centered tap transformer are more expensive than the diodes. So therefore a step down transformer reduces the size and cost. A centered tap rectifier is not as cost and size efficient as a bridge rectifier. So now, my friend Yousef will take over my place to continue our masterclass, beginning with DC to AC converters, aka inverters. Please, Yousef.
Hello.
Are you sharing your screen, or do you want me to direct the presentation?
Yeah, I can share my screen.
Okay.
If you,
right.
if you want to remove it. You need to make me a co-host. Hakan, are you here?
Sorry, what?
You need to make me co-host so I can share my screen.
I don't know how to do that, but okay, yeah. Now you're the host as well. Okay.
Can everyone see my screen?
Yep.
Yeah.
Okay. Next is like the DC to AC converters, which are the inverters. They're the future. They are the future, and they shaped our life pretty in a beautiful way. The conventional way to I wanted to say the conventional way of using rectifiers is using a motor and generator set, where we can change the frequency. But nowadays, we use the rectifiers and inverters to change the magnitude and frequency of our signal in power systems. Because, you know, we have 50 hertz in some countries and 60 hertz in some countries, and they're not compatible. So we need to change the frequency. The previous method is motor generator set. And it's very heavy, very expensive. So inverters and rectifiers combined, because we use both of them to generate, to change the frequency. They made it very simple to achieve that purpose. Also, inverters are used in electric cars, which is like 10 years from now, I don't think we will have any gas cars anymore, because electric cars are controlling the market. Like we saw, Tesla has the highest market out of any car manufacturer. Also, inverters are used in speed control of AC motors by changing the frequency of the motor. And they're very popular in solar system. Without the inverters, we cannot change the power. We cannot change the DC solar system into AC power, because, you know, solar systems, it gets the diodes of the solar systems converts the sunlight into DC. So we needed the inverters to change the DC to AC. That's what, so we can use it in the power system and control it and put it in the grid and use it in home, because inside the home, we have 220 volt AC. It's also used in uninterrupted power supply, which is very convenient for a lot of usage, for hospitals and a lot of places where we convert the DC batteries into AC power supply, and it is connected to the grid. So in case we get a shortage from the grid, the battery can change from DC to AC and feed the system of a hospital or very important places where we cannot lose power supply. And finally, we have the high voltage DC transmission lines, which are very, very, getting very popular, because their losses is very minimal compared to the high voltage AC transmission lines. And we can see this example, like the English channel between England and France. They use high voltage DC transmission lines, and without the inverters, it's simply impossible to do that unless we do a motor generator set, which is highly expensive. So the inverters is controlled using a drive. We use a drive to control. So the control signal is what defines what we get out of the inverter. So, you know, we can get a square wave, but a square wave is has high harmonic contents. It's a very bad waveform, very bad, because it contains a lot of harmonics and could damage our equipment and could damage the motors and the machines that we use. You know, harmonics, overpower, overheating. So it's not very popular to use the square wave or the quasi-square waves. These are controlled by the control signal that enters the transistors of the inverter, because the inverter uses transistors. It depends on if it's one phase or three phase, how many transistors are used. Then we have the quasi-square wave, and it's better than the square wave itself, but it's still not good. That's why we go to much better, also a bit more expensive than the complex and expensive than the square and quasi-square waves. And if we want to get like a real pure sine wave, that's impossible to do, but with pulse wave modulation topologies, we can filter out the harmonics and we can get almost good sine wave, but it's impossible to reach a really pure sine wave. Next is AC to AC cycloconverters. Of course, cycloconverters are AC to AC, so they are used to change the frequency and the magnitude of the voltage. Of course, the conventional way to do it is power transformer, but power transformer does not change the frequency. So it's only changed the magnitude of the voltage. The only way to change the frequency is, as I said, using the motor generator set. The main switch of the cycloconverters are the AC switch, which can be done using the triac or the anti-parallel connected SCR thyristors. Their application is limited to power system mostly, because they're not like home used and widely used in like your daily life. They're used by specialists and electrical engineering specialists mostly, using speed control of AC motors. We control the speed using the frequency, and the static VAR compensation, which is the power factor correction, the static tap changers, which are very important in electrical engineering. And these are the only that are used in the daily life, which is dimmers and flashers. They're very important, changing the frequencies of countries, and these applications is very important, as I said. And lastly, we have the DC to DC converter. The DC to DC converter changed the magnitude of the DC. As we can see here, we get a DC, we want to change its magnitude, the average voltage. That's how we measure a DC, using the average voltage. But why we measure the AC, any AC signal, we measure it using the fundamental RMS component. The DC to DC converters are used in widely used in electronics, data centers, and battery charging, LED lights, solar power generation. They're very widely used, especially in electrical vehicle systems, along with the inverter. Of course, does anyone know what is the conventional way of doing a DC to DC conversion? I suppose not. The conventional way of doing a DC to DC conversion is using a simple transistor circuit, multi-resistor circuit, which is voltage dividers, of course, because when we're using the voltage division, we change the magnitude of the voltage, and linear regulators as well, but they're very inefficient. The optimal switch for the DC to DC converters is a transistor. It provides self-commutation compared to the SCR thyristor. It needs a forced commutation circuit, which is heavy and not very good for, especially that it's mostly DC to DC conversion is mostly for electronics and small application. This is not very efficient to use an SCR thyristor. And we do have the energy storage buffer, which is simply a capacitor. It's a capacitor with an inductor, because we need the filter to smooth out the output of the DC to DC converter. Of course, there's always drawbacks to any electronic system, any device, there's always drawbacks. And maybe these drawbacks, I think the advantages outweighs the drawbacks of the power electronics, because these have solutions, but mainly it is the overload capacities. For short, there's no overload capacity for power electronics. You know, any machine in the world, when you first started, the rated current, the starting current is 5 or 20 times between these times the rated current. And we always design our systems and power electronics, we design our system on the I rated. We don't design it on the starting current, because the starting current is very large. Designing a system on a starting current is very expensive. So we always do it on the I rated. But in power electronics, the I rated, there's no capacity for overloading compared to machines and other machinery, which they can overload capacity for short times and sometimes long times, if you heard of power transformer overloading. But there's a solution for that, for power electronics, using the soft starters, which can reduce the starting current. Of course, power electronics, as we saw, generates harmonics, like in the square wave for the inverter, and in rectifiers, and in cycloconverters. We can reduce the harmonics as much as we can, but there will always be harmonics using in any system. Harmonics can be removed using filters and a lot of factors, but mostly filters and sharp filters to pick up our fundamental frequency. And also there is sometimes power factor reduction using power electronics and power systems, but it's very negligible. And if you use the right equipment, of course, we use very expensive equipment and very good controllability for especially power systems in countries. So it's not very something to be concerned about.